Hello and welcome to the next in the short series of videos about noise. This time looking at where noise comes from, the sources of the noise in electronic circuits. Well, we can divide these sources into three different types. First of all, intrinsic noise. This is noise that it's impossible to get rid of. It arises from the fundamental physical processes in the components themselves. And it's divided into shot noise, which happens in diodes and transistors in particular, thermal noise, which happens in resistors, and 1/f noise, which happens in op-amps, amongst other places. Second type of noise is ADC noise. That's analog to digital converter noise, or quantization noise. And there's a whole video dedicated to that one a little bit later in the series. And thirdly, extrinsic noise. That's noise that comes from outside the circuit. With good shielding and filtering, you can reduce extrinsic noise usually to negligible levels, unlike the intrinsic and the ADC noise, which is generated within the circuit itself and is impossible to entirely get rid of. The first type of intrinsic noise to consider is thermal noise, or sometimes called Johnson noise. And it's the noise that occurs in any resistor. Now, resistors are composed of electrons orbiting around nuclei, just like any bit of matter. And at any temperature above absolute zero, all of these electrons and nuclei are jiggling around at random. Occasionally, all of the electrons will happen to move one way and all the nuclei will happen to move the other way, and there will be a net voltage across the component, positive this side and negative this side. Other times they'll all jiggle around randomly and all the electrons will happen to move slightly that way and all the nuclei happen to move slightly that way, and that will result in a small noise potential in the other direction. And this noise potential is happening across every resistor in the world all the time. We can model this in a simulation circuit by adding a small additional noise voltage in series with every single resistor. And the magnitude of that additional noise voltage is given by this formula. That's in RMS volts, the square root of 4kTBR. K is a constant known as the Boltzmann constant, about 1.38 times 10 to the minus 23. T is the absolute temperature in degrees Kelvin. B is the bandwidth in hertz, and R is the size of the resistor itself in ohms. Multiply those together, take the square root, that gives you the RMS noise voltage in volts RMS. If you want it in volts per root hertz, you just take the B out of this equation and have E equals the square root of 4kTR, and that's the noise voltage in volts per root hertz. The second type of intrinsic noise voltage is called shot noise. So called because the process that makes it is similar to the process of taking a lot of shot, as in gunshot, tiny little pellets, and pouring them onto the floor. As the individual pellets land, in some seconds slightly more than average pellets land, in some seconds slightly fewer than the average number of pellets land. The result is the total number of pellets landing on the floor tends to vary with time, sometimes slightly above average, sometimes slightly below average. The net result is a slight noise signal on top of the average number of pellets landing on the floor. And exactly the same thing happens with electronics when you have electrons going across a barrier or a boundary. Some seconds, slightly more than average number of electrons flow over, and you get a slightly higher current just for that small amount of time. Other seconds, slightly fewer electrons than average go over, and you get a slightly smaller current. So while you get the average current, there are slight variations in the current with time, and those variations of current are the source of the shot noise. We can model it by having an additional noise current in parallel with a component like a diode, and the magnitude of that noise current is square root of 2qIb. Q is the charge on an electron, about 1.6 times 10 to the minus 19 coulombs. I is the magnitude of the current flowing through the diode in amps, and B is the bandwidth in hertz. And this gives you an RMS noise current, which you can add into a simulation of a diode to reflect the amount of noise that would be added to the system by the electrons going through that diode. Now there's one interesting thing about shot noise. It only happens in components like diodes or transistors. It doesn't happen in resistors. Not all currents have a shot noise component associated with them. Why doesn't it happen with resistors? Well, because in resistors there is an effect which cancels it out. Works like this. Supposing you've got a current flowing through a conductor, something like this. If at any tiny instance of time a few more electrons than average move across, say, this point here, remembering that the electrons are actually moving in the opposite direction to the conventional way that we indicate current, because electrons are negatively charged. So this current that we would normally draw like this is actually composed of electrons flowing the other way. So let's assume there's slightly more electrons than on average flow across this point in the circuit here. That would give this point here a slightly negative charge, leaving a slightly positive charge here. Now that would mean that there was an electric field across here going in this direction. Any electron in this bit of the conductor is effectively being repelled by the net negative charge of all of the additional electrons that have just moved across this boundary. And that results in a smaller current flowing in the next tiny instance of time. Similarly, if slightly fewer electrons than average moved across this boundary, there would be a net positive charge here and a net negative charge over here, caused by the greater number of electrons over here because they haven't moved across here yet. That would result in a positive charge over here, which actually attracts more electrons to speed up and move faster across this boundary in the next time period. This process happens so quickly that it effectively cancels out any slight shot noise component that might exist in the current flowing through a wire or a resistor. But when you've got a diode, then what we've got is a set of electrons moving from the conduction band of the N-type material down into the valence band of the P-type material. They're effectively jumping across a cliff. Any slight increase in the number of electrons that go over in a small interval of time isn't going to change the fact that the electrons up here are able to jump down from the conduction band to the valence band as they move across this PN boundary. So that's why we get shot noise in a diode and in transistors and other semiconductor circuits where you have this net boundary, but not in a wire or a resistor. The final type of intrinsic noise to talk about is 1/f noise, and it occurs in op-amps and other active components. Here we can see an excerpt from the datasheet of a TL071 showing the plot of the input noise voltage in nanovolts per root hertz against frequency. We can see that above 1 kHz, the power spectral density of the noise, the amount of energy in the noise at any frequency band, is pretty much constant. So it's kind of looking like white noise above 1 kHz. Below 1 kHz, however, there is an increasing amount of noise at lower frequencies. That is the effect of the 1/f noise. where the noise in volts per root hertz is proportional to 1 over the square root of the frequency, so that the noise power is proportional to 1 over the frequency, which is why it's called 1 over f noise. Next, quantization noise. Quantization noise is associated with the process of analog to digital conversion. Now, in any analog to digital converter, the output can take a finite number of different discrete values. In this case, we have a 3-bit analog to digital converter. Its output can be anything from 000 to 111, but it can only be one of those 8 possible levels. The input, however, can be any analog level at all within the range of the ADC. That means that when you do a process of conversion from the analog domain to the digital domain here, there is going to be an error introduced. And the error is the difference between the actual value of the analog signal and the output of the ADC, which would be the nearest one of these digital signals. That error voltage there behaves just like noise. It's an additional voltage that gets added onto our signal when it gets converted from the analog domain to the digital domain. Behaves just like noise. Now we move on to extrinsic noise. Extrinsic noise comes from outside the circuit, and it can get into the circuit using a variety of different routes. From the power supply, for example, anything that causes the power supply to a circuit to not be a constant voltage level, but to be oscillating up and down, can cause an unwanted noise signal in the output of an amplifier circuit. Hum, often related to mains pickup, usually a problem to do with insufficient grounding or not enough attention paid to get very low impedance ground paths in a circuit, can result in characteristic 50 Hz waveforms in a circuit as well. There's crosstalk and pickup, noise, that's noise coupling into the circuit from an adjacent external circuit, and that comes in via electric or magnetic fields. And finally, radiated noise, which comes in via electromagnetic waves from more distant sources. For example, radio waves, radars, that kind of thing. Both crosstalk and radiated noise couple into a circuit using one of 2 different routes. Firstly, the electric route. Any wire in a circuit effectively behaves like a radio antenna. A small voltage will be induced in it when an external varying magnetic field arrives. And these external electric fields can be part of the electromagnetic wave from an external radio source, or it can be coupling in from a varying potential difference across 2 nodes in an adjacent circuit. Or it can come in via the magnetic field, and as Faraday showed, any varying magnetic field will generate an electromotive force in any closed circuit. The magnetic fields could be part of an electromagnetic wave arising from a distant radio transmitter, or from the magnetic fields associated with an inductor or a transformer in an adjacent circuit. All of these produce routes for noise to enter a circuit. For electric fields in particular, you can reduce the amount of noise quite considerably by shielding. This is an electric shield over a sensitive part of a circuit, which is there to reduce the effect of any external electric fields on the sensitive circuit in between. Noise coupled in from the power supply can be reduced by careful filtering of the power supply as it arrives. You can get noise coupling in from communication wires as well, and careful filtering of the communication wires can help with those. External magnetic fields are somewhat harder to deal with. It's harder to shield them out, but you can reduce their effect with appropriate design techniques. That's all I wanted to say this time. Next video, we'll be looking at the characteristic power spectra of these types of noise and talking a bit about how to identify noise from their power spectra.